right, let's get started. Good morning, everybody. So we are going to be continuing off where we left on page 24, which is lesson 4. So if you want to title that, this is lesson 4. And your homework is in Khan Academy. So if you log into Khan Academy, you'll see 3 little mini assignments in there. Most of it's just multiple choice on identifying some asymptotes and such. So watch this lesson and then go on to there and let me know. Today we have our pre-calculus office hours from 1 to 2. So if you have any questions, let me know there. All right. So rational functions. Let n of x a numerator and d of x a denominator be polynomial functions where d of x cannot equal 0. So then a rational function is considered r of x equals n of x over d of x. So this is all going to be stuff that you know. Now we're just giving it our function notation. I'll zoom in a little bit here. And let me know if the volume's not good, because I can always turn it up. So the domain of x includes all real numbers, except the values that can cause division by 0. So as we know, dividing by 0 is illegal. We cannot do that. Nothing new there. Domain restrictions come from the values that make the denominator 0. Okay. So example 1 says find the domain for the following function. So what we're going to do is we're going to take our denominator and we know that it's not allowed to be 0. So we're going to find exactly what x values that happens at. So we're going to factor this polynomial. So we get x minus 2 and x minus 1 not allowed to be equal to 0. You can drop down your t-chart. So we know x cannot be equal to 2 and that x cannot be equal to 1. When that happens, we get vertical asymptotes. Which makes sense because x equals lines are vertical lines, so therefore vertical asymptotes. So if we want to state our restricted domain, we're going to use that fact. So we know from negative, forgot my parentheses. We have from negative infinity to 1, not inclusive, unioned with from 1 to 2, non-inclusive, and unioned with 2 to infinity, again non-inclusive. We can't include those 2's and 1's because that's going to be our vertical asymptotes. Not allowed to touch those points because we will get an undefined denominator. Okay. So vertical asymptotes, as previously stated, are going to be x equals some value a, whatever it may be. In the uppercase, it was 2 and 1. Okay, so the graph behavior will approach the vertical line and either increases or decreases without a bound. So, what is a red highlighter? That's weird. So this is literally, oh, went too far. This is literally the definition of a limit. This is what a limit means. What are we approaching? So we have our function. So it says limit as x approaches a from the left, that little negative here means from the left will be either positive or negative infinity. And as x approaches a, that little plus sign means from the right will also be either positive or negative infinity. You just have to follow the curve to be able to figure that out. So, let me put a line here. If we use our graph off to the side, we can see that there are some vertical and horizontal asymptotes. So it looks like, actually let me draw on those axes a little bit darker. It's kind of hard to see them. So sketch those in. My line's going to be a little dodgy here, but that's okay. That's our axis. All right, so we can see we have a vertical asymptote here. At x equals -3. And we have a horizontal asymptote here at y equals 1. So let's sketch those in. That's going to help us out. So let's do some limits. So let's do the limit as x approaches -3 from the left of that function f of x. So in this case, you want to take your pen and you're working from the left and you're seeing where does that curve take you. So if I look here and I'm at the left, make this a little bit of a brighter blue. I already used that color. If I go from the left and I'm following the function, it's going up and up and up. And since it's going higher and higher and higher, that means we must be approaching positive infinity. And let's go from the other way as well. So let's do the limit as x is approaching -3 from the right of that function. So for this, we need to go all the way to the right and see where our curve takes us. So I'm all the way to the right, and I'm following my curve, and I'm going down and down and down and down and down, which means I must be approaching -infinity. Okay. So, horizontal asymptotes. Horizontal asymptote is as y equals approaching some letter or number b. In the example to the right, we see that it's +1. The graph will either lend itself towards positive or negative infinity, as we've been practicing. And it is possible to cross a horizontal asymptote. We're going to see that on a page later on in this lesson. So it says that is the limit as x approaches -infinity. So if we want to write ourselves a little note here, this is as x is getting smaller, what is y approaching? That's what this question means. So as x is getting smaller, what is y approaching? So if we go on this graph again, if we're getting smaller and they're x's, that means we're working our way to the left. So we go all the way to the left on this picture. The leftmost curve looks like it's getting closer and closer, but it's not actually going to touch that line y equals 1. So that's going to be a 1. And then the other one says as x, I'll zoom in, as x is getting larger, what is y approaching? So these are kind of unique cases where we're talking about what asymptote line are we approaching. Sometimes I was above, we got answers of infinity, but here we're actually getting a specific point. So as x is getting larger, that means I'm going to the right on my graph. So if I look at that function that's going more right and right and right, I see that I'm also getting infinitely close, but won't actually touch that line y equals 1. Okay, give you a second to get that down. I'll zoom out a little bit for you. Okay, now flip the page when you're ready. Okay, and again, this is going to be posted on YouTube, so if I'm going too fast, don't panic. Or just tell me in the chat, hey, slow down. All right, so There's 3 cases in which we will get a horizontal asymptote. 3 cases. Case numero uno. A numerator degree is less than the denominator degree. If this happens, the line y equals 0 will be your horizontal asymptote. So an example of this, I don't know, could be like y equals x minus 2 over x squared minus 6x plus 10. So our numerator has a degree of 1, but our denominator has a degree of 2. Therefore, since the denominator is bigger, our horizontal asymptote will be y equals 0. Case number 2. The numerator degree is equal to the denominator degree. So in this case, the ratio of the leading coefficient is a horizontal asymptote. So an example I'll give you for that one is maybe we have 5 minus 8x squared over 2x squared plus 3x minus 4. And I did that on purpose, not being written in standard form on the top, because we need to make sure we're taking the sign along with it. So it's going to be a over b. So a is going to represent the leading coefficient for our numerator, and b is going to represent the leading coefficient for our denominator. So a is going to be negative 8 for this case, and b is going to be positive 2. Therefore, we get negative 4. So y equals negative 4 would be our horizontal asymptote for this specific case. But that ratio, y equals a over b, definitely going to need to know that. All right, in case number 3, the numerator degree is greater than the denominator degree. That means the graph has no horizontal asymptotes. So maybe we have x squared minus 5x plus 4 over x plus 1. The numerator degree is 2, the denominator degree is 1. That's it. Now, this isn't saying there is a spot where this is undefined. There might be a hole in the graph, but it doesn't mean there's going to be a specific horizontal asymptote. Okay. So those are your 3 cases, and we'll be referencing them in the next few examples. So, graphing rational functions. It will become important as we move through our course to be able to analyze functions completely without access of a graphing utility. You should begin to develop some procedural thinking to help you along this pathway. So when you get to calculus, there's going to be a lot of sections on exams and such that will not allow you to have a calculator. There's calculator sections and there's non-calculator sections, and that will happen to you whether you're taking AP or just your university calculus. So we need to know how to do this without that aid. So this one's in factored form. How nice. That was too nice. So graph each rational function and analyze. All right, so first we want to think of, is this case number 1, 2, or 3? So my numerator doesn't have any x, so it's really a degree of 0. And my denominator, if I simplify that out, is going to be x squared. So this is really like 2x to the 0 over, and I'll just simplify that out because why not? So therefore, this is case number 1. Case number 1. Numerator degree is less than the denominator degree. All right, so there's some information we want to lay off to the side. So is there an x-intercept? Sometimes there is, sometimes there's not. So if we have an x-intercept, that means on the x-axis. So we have to think what value is going to be 0. It's going to be our y value. It's going to be like 5 comma something. 5 comma 0 is an example of a root. So if we did that, we would have like 0. I'll put this as 0 over 1 equals 2 over our polynomial. Now if I go, if I go to simplify this, I'm not going to get a real answer, right? So therefore, there is not an x-intercept. And that's okay, no big deal. How about a y-intercept? So if I have a y-intercept, that means I have 0 comma something. So anywhere I see an x, I'm going to plug in a 0. So that's going to be like 2 over 0 minus 2 0 plus 3. And it really doesn't matter if you use the factored one or not. I like the factored one. So we get 2 over, what's that, negative 2 times 3. So 2 over negative 6 is going to be negative 1/3. So our y-intercept here is 0, negative third. All right, so let's talk asymptotes. So thanks to them giving it to us in factored form, that kind of gives us what our vertical asymptotes are going to be really nicely, because our denominator can't be equal to 0. So if we have our x minus 2 and x plus 3 can't equal 0, and I do my t-chart, I get x cannot equal 2 and x cannot equal negative 3. So therefore, those are our vertical asymptotes. So our vertical asymptote, x equals 2, x equals negative 3. Horizontal asymptote, because this was case number 1, it's going to be y equals 0. Holes, there are no holes for now. We're going to see some examples where there will be holes, but for this one, there is none. And let's think of our restricted domain, just like we did on the previous page. So we are going to be using our vertical asymptotes in this case to help us out. So we're going to go from negative infinity to negative 3, non-inclusive, from negative 3 to 2, and from 2 to infinity. For the range, we're going to use our horizontal asymptote, which we see is 0, so that's going to be, no, it's a bad infinity sign, isn't it? Negative infinity to 0, and then from 0 to infinity. All right, so on our graph, let's draw our asymptotes. Is that a union? Yes. Yes, it is. It is a union. All right, I'll give you a second to get that down. All right, so I'm going to sketch these in. So we have x equals 2, and hopefully you have a straight edge. I do not, so my lines are going to be super sketchy, but that's okay. I'm going to do these as dashed so I don't get confused with the function that we're going to draw, but I'll label them. So we got x equals 2. We also have x equals negative 3. So again, I'm doing these dashed so I don't get confused. And what do I got? Y equals 0. Ooh. No, my lines aren't going to be straight, but that one was real bad. Okay. Y equals 0. Okay, so we got our asymptotes down. So now you might be thinking, okay, cool. Well, what's the curve going to look like? Because you told me I'm not allowed to use my calculator. We're going to use something called testing intervals. So, test intervals. And you won't always have to do testing intervals. We're going to see an example later on where we don't really need it. So let's see. We do know that one point is 0, negative third. We have that y-intercept. So that's nice. So I'm going to graph that on there. I'm going to use a brighter color so it's easier to see. So that's about there. Now, since I know that I can't cross that line y equals 0, this must be a downward facing curve. A little frowny face there. So that's part of our function, but there could be more to it. That's just part of it. So in our testing intervals, I'm going to use my vertical asymptotes so I know what's happening before and after them. So we know we have negative 3 and 2. Now I'm going to pick a point before it, in the middle, and after those intervals. I'm going to test it into my function and see if we get a positive or a negative answer. That's going to tell us if it's going to be above or below the axis. Thanks for following. By the way, Lemon SSBU, you don't have to tell me your name, but can you put your initials? Because I don't know who you are. I'm just curious, who's joining me in this live. So I'm not going to pick exactly negative 3 because we know it's already going to be undefined there. So let's pick negative 4. go crazy, right? And I'm using that original f of x up top. So let's see, we're going to test negative 4. So we're going to have 2 over, let's see, we have negative 4 minus 2, negative 4 plus 3. So sorry, I'm kind of squishing my work here. 2 over, we have negative 6 times negative 1. I don't really care what the value of that is. I just want to know, is my final answer going to be positive or negative? And negative times negative is a positive. So I'm going to put a plus sign here. So we know that's going to be above the graph. Then I'm going to pick a point in between negative 3 and 2. Let's say 0, because that's a nice number, right? So let's test 0. So we have 2 over 0 minus 2, 0 plus 3. So we get 2 over negative 2 times 3. So that's going to be a negative answer, which we saw our graph was below there, so that makes sense. Means we're doing something right. And then I got to pick a point after 2. So let's just test like 3. You know, doesn't really matter. You could pick a million if you really wanted to, but I'm just picking easy numbers. So we have 3 minus 2, 3 plus 3. I can already see that's going to give me a positive. So again, with the testing intervals, oh, that's going to be too light. Positive is going to be above. Negative is going to be below. I'm only in math. Oh, cool. Well, thanks for popping in. You know, my husband and I are both doing some math streams because, you know, we're not allowed to be at school right now. So why not do math on Twitch? All right. So we said before and the left hand is going to be above. So we could have, let me go back to my blue color, be some sort of curve. And again, we're approaching those lines. We're not actually touching them. And then similarly, we're still above and we're still approaching both of those. So it doesn't matter that the slope is necessarily positive or negative. It just means we need to be above or below the x-axis. All right, we're going to do one example on the next page. So on page 26, you're going to cross off example, the limits and slanty slopes. We're just going to do example 2b. Oh, side note, Lemon SSBU. On Sundays, starting this week Sunday, we're going to be, my husband and I, since we're both certified in math, we're going to be having Sundays with the Sadlers. So if you're working on any math and if you have a question, you're not sure how to do something, you can send us a message and we can help you out. So if you tune in on Sundays, do the high school time slot though, we can help you out with any math questions that you need via this Twitch stream. All right, this case is fun. So we still want to find all that information. But if you notice, when we look at this function, we have a quantity of x minus 2 on the top and a quantity of x minus 2 on the bottom. So that would simplify out, wouldn't it? It's gone. So we really have g of x is 2x minus 1. But you might be thinking like, why'd they give us that? This is a case where we are going to have a hole. A case where we're going to have a hole, okay? So I'm actually going to skip around a little bit. So, and you notice that this is also going to be linear. So we're going to be graphing a line, but there's going to be a hole in that line. Sounds awesome. Quick question. Is this for class or more for fun? This is my pre-calculus class. I am making them do some new topics. We're not going crazy every day like we normally would in school, but I'm going to be doing a couple new topics with my students each week to keep them engaged and so we don't fall too far behind, especially because a lot of my pre-calc students will be going to college next year and I want to make sure they have the base knowledge that they need. So, the whole. If we know x minus 2 cannot equal 0. So that means x cannot equal 2. So for my whole, that's going to be the x value in it. And then you might be thinking, all right, well, what's the output going to be? Well, if this is a line, we just plug and chug. So we have g of 2 equals 2 times 2 minus 1. So g of 2 equals 3. So there's going to be a hole at the point 2, 3. All right, let's go back to going in order. Though why not skip around? There's no law saying I have to go in order. All right, an x-intercept means that our y value is going to be equal to 0. So 0 equals 2x minus 1. So when the dust settles, we should get x equals, oops, hold on. Sorry, I'm kind of squishing this in here. So we're going to add 1. Ah, my marker. Okay. So we have x equals half. So that's going to be 1/2 comma 0. Sorry for the color parade that's happening on this page, but you know, hopefully your notes look a little nicer than mine. All right, and our y-intercept means our x is going to be equal to 0. So g of 0 equals 2 times 0 minus 1. So g of 0 equals negative 1. So we have 0, negative 1 there. And because this is linear and we already took care of the whole, there's not going to be any asymptotes. It would help if I could spell. Whatever. We know I don't teach English. You would not want me teaching you English. That would be so bad. So bad. All right. And let's take care of some domain and range business. So we know we have our whole, so we got to keep that in mind. So our domain, our x values, we're going to be dealing with negative infinity to 2 and continuing off at 2 to infinity, again, non-inclusive. And then our range, looking at our y values, that's going to be 3. So we're going to have negative infinity to 3, and then 3 to infinity. All right, give you a second to get that down, and then we're going to start graphing this baby. Okay. Now I don't need to do any test points or anything because I don't have any asymptotes. I just need to remember when I get to that point 2, 3, I'm going to put a hole there. But other than that, it's pretty much just like graphing a line. So let me pick a bright color so it stands out. So we know we have 0, negative 1 as a point, and we know we have 2, 3 as a whole. So I'm just going to make that an open circle. And this line has a slope of 2, so up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and it keeps going on and on and on. So we can just connect our line. Okay. Very good. All right. If you're in my class, you're going to flip the page. I'm not doing those next 2 examples, so you can cross them off. So cross that off, cross that off. All right. Graphing a rational function. Oh, I heard a noise, but it was just my husband getting an email. All right. So we have our function. What I want to do is I'm going to factor this, because why not? So we have f of x equals x minus 3 all over x plus 3 and x minus 2. I wanted to factor it to see if anything would simplify out. In this case, it doesn't. That's okay. No big deal. No big deal. So there's a bunch of info. Ooh, I didn't want red. Red's such an aggressive color. We need to find our x-intercept. So our x-intercept means our y value is equal to 0. So I'm going to have 0. I'm just going to put it over 1 so we see that math a little bit nicer. Over x plus 3, x minus 2. If we cross multiply, there we go. We get, that cancels out. 1 equals. Oh wait, not 1 equals. Hello, Sadler. Wake up. Have your coffee. I did not have coffee yet, so, you know, it tells you how my day's going. So, we get 0 equals x minus 3, which means we get x equals 3. So our x-intercept is going to be the point 3, 0. So if we want, we can graph that right now as we go along. Let's find our y-intercept. So we have a y-intercept, that means my x value is equal to 0. So we have 0 minus 3 over 0. I'm going to use the other one. I like the factored one. I guess it doesn't really matter. I've already committed. We're going in. So we get negative 3 over negative 6, which means I'm going to have positive half there. So therefore, we have 0 comma 1 half. You can plot that point if we want as well. About there. It's not going to be perfect. All right, and now we got to look for some asymptotes. So let's do vertical asymptotes first. It's a sad day. All right, so it's when our denominator cannot equal 0. So we already know we have x plus 3 and x minus 2 cannot equal 0. So therefore, our vertical asymptotes are going to be negative 3 and positive 2. So if we want, we can sketch those on there. And again, I'm going to use dashed lines so I don't get confused with my original function. So negative 3 and positive 2. Okay, so I recommend dashed lines for that. And then we're gonna look for our horizontal asymptotes next. So horiz ASY. Okay, horizontal asymptotes next. Well, if we look, we have an x over an x squared. So we got to think of what case is that from the other page. This is going to be case number 1, which means we're going to have y equals 0 as another asymptote. Now, you might be thinking, oh snap, but there is a point on that asymptote. This is a rare case where it is actually okay. That just means that there's a little exception there. So that point is still going to exist, but nothing else on the function will be allowed to touch the asymptote. This is just like a really weird exception. All right, so we've got our asymptotes graphed. We've got a couple points going there. So we need to do a test to see what's our curve going to look like. Now I bet the one in the middle where I have that y-intercept, I bet that's going to look like a smiley face, but we'll just test it to be safe. Okay? Where do I have room to do a test? That's a better question. I'm going to do it over here. All right. So, testing intervals. And again, I'm going to use those asymptotes. So we have negative 3 and 2. And we've got to pick points that are before, between, and after. We can't pick exactly those because we already know it's going to be undefined. So let's say I'm going to test negative 4 on the left, okay? So if I tested negative 4, that means I would get like negative 7 over negative 1 times negative 6. And I'm just plugging that back into the one that I factored out because it's a little bit easier. So therefore, all of that, I don't care what the answer is. I just care about its sign. So that's going to be negative, which means it's going to be below the x-axis, okay? Next, I like to use 0 because it's a pretty point. So if I test with 0, I'm going to get negative 3 over, let's see, 3 times negative 2, which that is going to be a negative over negative is going to give me a positive. So that's going to be above. So our hypothesis that that's going to look like a smiley face in the middle was right. And then after, let's just pick, I don't know. Let's pick 4. If I pick 3, I know I have a root there, so that's not very exciting. So let's pick, say, 4. So if I picked 4, is that 4 minus 1? I could just write 3. 3 over 7 times 4 minus 2 is 2. So that is going to be positive. Now this one, that space is a little bit interesting because we can approach those asymptotes. So when I go to graph this, it's going to be this one's a little bit special. Oh, how'd that line get there? Go away. All right, so we said in the middle, it's positive. That's going to be smiley. Hopefully yours looks less sketchy than mine. On the left, we said negative, so that's going to be falling in between those. So approaching both of those asymptotes. Wow, that curve is really bad. I can't let that stand. Whee! That's a little bit better. Fine if you say we, it goes easier. And then on the right, this one's a little bit interesting because we are going to go above, but we also could approach that asymptote. So this one's a little bit special. This is special. Okay, special case. Very good. One more example, and then we'll call it a day. Sorry, this lesson is a little bit longer. Graphing tends to take longer. So hopefully our future lessons won't be too long. But we're almost done. Hang in there with me. Hang in there. All right. Find the intercepts, asymptotes, etc. So we've got our function, and I'm going to factor this right away. So f of x equals x minus 4 times x plus 2 over, we got difference of two perfect squares, so x minus 2 and x plus 2. As we see here, we have some stuff that simplifies out. When this happens, that means we're going to have a hole. Specifically, it would be at negative 2 because you have to set it equal to 0. So hole at negative 2. We know it's going to be the x value at least. We don't know what the y value is going to be. So our function here, if I continue simplifying it, is x minus 4 over x minus 2. A little bit nicer to look at. A little bit. All right. Let's find some information. So, x-intercepts, again, that's like when you have x comma 0. So our y value is equal to 0. So 0 over 1. I'm going to use the simplified one because, you know, why make my life harder if I don't have to? So we cross multiply. When the dust settles, we get the we get the x-intercept of 4, 0. So if we want, we can plot that over here so we don't forget about it. Okay. And then y-intercept, remember that's like 0 comma some y value. So I'm going to substitute in 0 for my x's. So I have 0 minus 4 over 0 minus 2. When that settles, we're going to get the point 0, 2. Oh, that got spaced out weird. 0, 2. So we can plot that point as well so we don't forget about it. And we know that, oh, what happened? Okay, that was weird. I'm still getting used to the iPad, so bear with me, people. All right. And we know we're going to have a hole at negative 2. We're just not exactly sure what that pretty point's going to be. So let's find some asymptotes. Vertical asymptote. That's when your denominator cannot equal 0. So therefore, our vertical asymptote is going to be at x equals 2. So let's sketch that in. And again, just as before, I'm going to be using dashed lines so I don't get confused with my function. Let's draw that in. X equals 2. Our whole, this isn't linear, it's going to be 2 comma, or excuse me, not 2, negative 2 comma some number. And then let's deal, oops, wrong color. Let's deal with our horizontal asymptote. This is going to be case number 2. Because we have the same degree on the top and the bottom, so we have to use that y equals a over b, the coefficient for the numerator, divided by the coefficient for the denominator. Because it's x minus 4 and x minus 2, or even if you use the original, we have x squared and x squared, both those coefficients are 1. So if we did that, we really have 1 over 1. So therefore, y equals 1 is going to be another asymptote. And I'm going to sketch that in with dashed lines. Y equals 1. Now, you could do test points if your heart so desired, but based on what I'm looking at here, I mean, you can see like where the curve is going to be, and we have to still keep in mind that we have to pass that vertical line test. So because I'll write a little note down here. So because we know points on the graph, we don't need the interval test. So because we know a bunch of specific points, we're pretty good. And we do need to specify, we know that there's going to be a whole lot -2 something. So when I'm drawing in my curve, I just need to keep in mind, ooh, that was a bad curve. Go back. Just need to keep in mind I have a hole there. And then over here we have this point. So we're going to be approaching, but not touching both of those. So, and it passes the vertical line test. So your homework is going to be in Khan Academy. Office hours today from 1 to 2 for pre-calculus, or if you want to catch me on my morning office hours from 10 to 11 tomorrow, that's fine too. But I hope all of you have an awesome day. Bye.